Today we're going to sort of build a bridge from the world that you're used to, the bulk world, to quantum mechanics. And it didn't just come out of nowhere. So we're going to talk about the thinking that drove us to this bizarre set of theories that we call quantum mechanics. So it's a lot of history. There's maybe 4 points in this presentation that I really want you to remember. So for the most part, just sit back and think about the history. We're going way back, okay? But when it's something that I want you to retain, I'll let you know. And I'll say, okay, this right here is what you need to take home with you. But the rest of it is just to provide a historical context for where we are in this class, okay? So we're going to go from classical mechanics to quantum mechanics. Now, the word mechanics in physics is just the mathematics, the theory behind the motions of objects, right? So when you took mechanics, you did cannonballs and pendulums and so on. So that's what classical mechanics is. When we get into quantum mechanics, it's the mechanics of waves, how waves explain the behavior of systems. So that's what the word mechanics is. Classical is Newtonian, and quantum is quantum. So Schrodinger and Dirac. So we'll get into this whole transformation as to why we needed it in the first place, and then how the theories came about. So way back before Einstein, before Schrodinger, before Boltzmann and Planck, and even before Newton, we had René Descartes. Now you know part of that name. The Cartesian system of geometry is named after him. Okay. So you know about Descartes, you know about geometry, and that's why we know about that, because he's one of the first ones to really think about mathematics being useful. He was really a philosopher, but back then philosophy and science were tied together. Philosophy was just trying to think about how things work. And Descartes said there's a method, we need a method for finding out the truth as we think about these things. And so then as he was writing Rules for the Mind, he said he was thinking about the mind, and he said that it has something in it which we might call a divine spark that gives us these germs of useful modes of thought. Now, he didn't really have germ theory at the time, but that's maybe this idea of a small thing that grows into something larger. That's when we started adopting the germ theory. We said, yeah, germs are this small thing that develops into something larger. So he was just putting this idea of useful thoughts being communicable, right? You get a good idea, and then your friend gets it because it was a good idea, and it passes on from person to person. And so then later he wrote his work, Geometry, and it was his work in geometry that inspired a young Newton to study math. So that's pretty cool. We know about Newton, and Newton's supreme in terms of physics, but he got the idea to use math to describe the world from Descartes in his book, Geometry. So this germ of a useful mode of thought that mathematics was useful went from Descartes to Newton. And Newton, it's hard to exaggerate how influential Newton was. You guys know this. You know that Newtonian mechanics, and that's all of our physics that we deal with in terms of the large-scale objects like baseballs and cannonballs and cars. We even use it on the police force and forensics. When two cars crash, they get out the protractor and they get the angles and the speed, and they do skid mark analysis and so on, and it's all using Newtonian physics. So if you're a forensic chemistry major, that's really not forensic chemistry, but that's forensics and criminalistics. So Newtonian physics was supreme, and you know that you've arrived when you're not just popular among the science community, but poets start writing poems about you. Okay, so probably the foremost poet in England was Alexander Pope, and he was trying to describe the greatness of Newton, and so he wrote, "Nature and nature's laws were hid in night, and God said, 'Let Newton be,' and all was light." Okay, so I mean, he's saying God didn't just say, "Let there be light." He said, "Let Newton be," and then everything was illuminated. So that's pretty amazing when you're that popular and that renowned that the poets of your country start writing poems about you and how influential you are. So this is what we have. We have René Descartes passing on that germ of useful thought of mathematics to Newton. And then Newton passed that on to Boltzmann. Boltzmann in the late 1800s used the math and introduced this idea of quantized energy levels or velocities of gases. And in his paper, he said, I don't really mean that gases would have fixed velocities, but it's easier to do the math if we just first assume that they're discrete values. And essentially, he was doing by hand what we do in Excel. Okay, you have your formula, right? It's a continuous formula, but we just make a table with 10 or so values in it because it's easier. We can calculate 10 values versus an infinite number of values very easily. And that's exactly what Boltzmann did. But your table, are you saying that whatever equation that you're doing is discrete and it only has 10 possible values? No, you're just using it as a mathematical simplification. And that's what Boltzmann said. It just simplifies the math if I assume that there are fixed values. Basically, I'm using a table to do my math. But this idea of quantized values actually helped Planck fix some of the quantum mechanical problems. Okay, so Planck got this idea of quantized thinking from Boltzmann. So a lot of people say Max Planck is the father of quantum mechanics, but I really think it was Boltzmann, because it was his first paper in deciding that I'm going to treat gas velocities as if they have fixed velocities, and that was the first time somebody did the math related to quantum mechanics. Then math was passed from Heisenberg to de Broglie, and then de Broglie was thinking about the problem, which we'll get into, of how the electron moves around the nucleus, why it doesn't fly away, and why isn't it sucked into the nucleus. And he was thinking about the motions of this electron cloud, and he loved music, and particularly the violin, and he was thinking about waves. And he said a standing wave is something that is stable, and maybe the electron cloud acts like a standing wave. So he passed that idea, a germ of useful thought, onto Schrodinger, and Schrodinger with math and added mechanics to it, the math behind waves, and then Dirac. So Dirac is the one that's really solved all of our problems. We talk about the Schrodinger equation, but Dirac is the one that completed it for multiple electrons. So this is sort of an overview of this thinking as it went from person to person throughout history. Descartes and Newton were in the 15 and 1600s, but then Boltzmann in the 1800s, and all of this, Schrodinger and Dirac in the early 1900s. So let's talk about Planck's work. And this is one of the areas that I need you to pay attention to and retain. There's this concept of black body radiation. And think of your stove burner. If you have an electric stove burner, when you plug it in, okay, it starts to get hot, and then it starts to glow orange, and then red, and it gets maybe even a brighter red, almost white. We don't have the wattage typically in a household burner to turn it white hot, but it could theoretically get white hot, where it's emitting all wavelengths of visible light. Now, the interesting thing about black body radiation is the spectrum that's coming off of that hot object is the same no matter what it's made of. That's weird. That was a weird thing. Why does it not depend upon the material? It just depends upon the temperature. So this was a curiosity in science for a long time. Think about how far back mankind has been heating up metal to make swords and implements, and seeing it glow. And it's the same glow whether it's steel, bronze, straight iron, it's the same glow. So that's bizarre that it would be the same glow. So black body radiation was something that was strange. And if you looked at the chart, this is the spectrum of a black body radiator. Okay, this right here, this is the spectrum here of a black body radiator. In the infrared, well, first of all, let's go to Wien's displacement law. So Wilhelm Wien in 1893, he found the maximum here, and he tracked that with temperature, and he said, oh, okay, it's nice that this maximum value is inversely related to temperature. So if it cools down, then the maximum slides to a longer wavelength, lower energies, and if you heat it up, the maximum gets to smaller wavelengths. So that's Wien's displacement law. And then Rayleigh and Jeans, they, in 1905, fit the data in the infrared to this law right here. Okay, so they said that the energy emitted here, it drops off as 1 over the wavelength to the 4th power. Now let's speak briefly about the difference between a theory and a law. Okay, a lot of people think a law is higher than a theory. It's actually the opposite. A law just fits observation. You don't know why, and you don't really have a theory associated with why. A theory tries to explain why, but a law is just fitting observation. So this is the Rayleigh-Jeans law, but it's actually lower than a theory. When Planck came up with this, it's really the black body theory of radiation. Like it matches the data and explains why. But the Rayleigh-Jeans law just fits the data with no real explanation why. You just have an equation that fits the data. And then Planck came along and used the idea of Boltzmann. So notice it's pretty close to the same equation. We still have wavelength in the x-axis, in the denominator, okay? And it's gone up by a power, lambda to the 5th, but then there's a lambda term in here, okay? But this piece right here is Boltzmann's math. So this idea that the wavelength compared to the energy of the room, the temperature that you have, that's the math straight out of Boltzmann's paper. And so where did that math come from? It came from Boltzmann saying that particles could only have certain energies. So that's pretty strange that assuming the particles had quantized energies fixed the black body radiation problem. And so that's what I think you should write down. That assuming that particles had fixed energies solved the black body radiation problem for Planck. Assuming the particles had fixed energies, quantized energies is another way to say it, fixed the black body radiation problem. And the number that came out of that was Planck's constant. That's why it's got his name on it. Okay. So this idea of this black body radiation led to this term that you'll hear people when they talk about the quantized effects and quantum mechanics versus classical mechanics, they'll use the phrase the UV catastrophe. Okay, that sounds kind of strange. What's catastrophic about the UV light? Well, physics thought they understood black body radiation. They had the Wien's law and they had the Rayleigh-Jeans law, and that worked in the infrared. Okay, but when they extrapolated it to the UV, so here the Rayleigh-Jeans law was good down here. Okay, so this is good, right? But when you go to short wavelength into the UV, the Rayleigh-Jeans law predicts infinite emission of light. Okay, so when you predict something goes to infinity and it really goes to zero, mathematically or scientifically, that's a catastrophe. So that's why they say this is a catastrophic error for Rayleigh and Jeans in the UV. Okay, so that's where that term comes from, the UV catastrophe. Classical physics sort of described it going to infinity, but quantum mechanics fixed it to where it actually goes back to zero in the UV. And so we can use infrared light. We know that infrared light is a function of temperature. So if things are different in temperature, then there'll be a contrast. So I'm hotter than the wall because my heart's beating and I'm consuming the sugar that I ate this morning. Okay, and so I'm going to be emitting light in the infrared more than the wall is. And that's where our night vision comes from and so on. Like this is a thermal camera and it's able to see right through that plastic bag. All of our night vision is based on this technology. And so essentially what I've said, that when they extrapolated the Rayleigh-Jeans law to the UV region, the predicted energy emission went to infinity. So Planck solved the black body radiation problem and was given the Max Planck medal. Actually, he was given eventually the Nobel Prize. And he said this idea of quantized energy from Boltzmann was an act of desperation. Now, how many of you have struggled with a math problem for 6 years? That's dedication. So he'd been studying other things, of course, but he struggled with this black body radiation. He knew he was kind of on the track of solving that problem. And he didn't want to violate the conservation of energy. He didn't want to violate the laws related to entropy and spontaneous processes. But he saw the math of Boltzmann, and he said, maybe that'll fix it. And sure enough, it did. But out came this quantized amount of action, this Planck's constant. And what was the justification for that? Well, is it just a mathematical trick? Was it just a number that fixed the black body radiation problem and that's it? Well, it was confirmed later when we looked at black body radiation. When we looked at the photoelectric effect. This was an exciting time in physics. I don't know how many of these folks you remember from physics, but a lot of their names have popped up, and they're also popping up in chemistry. So in 1911, this guy, Ernest Solvay, he's right here. This is Solvay. And he was a rich guy that had a huge estate, and he liked physics. And so he would just invite all of these physicists to come and stay at his estate and have conferences and talk about their research at the same time. So pretty cool event. And so we have a lot of famous names in here that you've maybe heard of. Now I've talked about Max Planck, and I've talked about de Broglie here, Maurice de Broglie. He was a young guy compared to the others. His contribution in terms of waves was written in his doctoral thesis. So he wasn't even a full-blown scientist yet, and he came up with the idea of waves. Maybe you heard of, we've talked about the Rayleigh-Jeans law. Here's Jeans here, and number 3, where's he? Yeah, right there. And then Ernest Rutherford, he's the discoverer of the nucleus. So in freshman chemistry, they shoot alpha particles at gold foil, and he discovers the nucleus. That was Rutherford. So he was at the Solvay conference. And here's Einstein. What a young-looking Einstein we have here. Not this crazy hair still, but not gray. Okay, so that's pretty neat. I have this on a coaster. I'm such a nerd. But anyway. And then down here, it's the people that are seated. Over here is Walter Nernst. Now, I don't remember if you remember from Gen Chem. I think it was Gen Chem 2, where you did the electrochemistry thing, and you had the Nernst equation. So electrochemistry, he's one of the fathers of electrochemistry. And then here's Wien, Wilhelm Wien. And then here's Marie Curie. So she was she wasn't the discoverer of radiation, that was Röntgen, but she was the one that extracted a lot of radioactive elements, essentially in a garage at the Sorbonne University in Paris. So she was a fantastic scientist and used the same extraction scheme that we still use today in freshman chemistry for isolating the different cations. And so she had, they knew that uranium was in pitch blende, sort of some mine tailings, and she extracted uranium from train car loads of pitch blende. So was Planck's constant just a mathematical trick to fix black body radiation, or was it really a fundamental piece of nature? The photoelectric effect showed that Planck's constant was fundamental to nature. So how did it do that? Well, if you hit a piece of metal with high energy light, it emits electrons. Here's a word for you because we're going to use it the whole semester. It's called a photoelectron. We have the photoelectric effect, and then we have photoelectron spectroscopy. So we're going to be talking about photoelectrons a lot this whole semester. If you want to know how deep the electrons are in the electron cloud, you can use X-ray photoelectron spectroscopy. So photoelectrons are an important concept and a tool for learning about molecules and learning about atoms. So get in your head this idea of you shine light on a substance, some of those photons of light can get absorbed by an electron, and the electron comes shooting out. That's called a photoelectron. Now, if you increase the frequency of that light, then the electrons come out with more kinetic energy. If you decrease the frequency, they come out with less kinetic energy. If you increase the intensity of the light, in other words, you have a brighter light, it doesn't change at all. You just get more electrons. So this photoelectric effect is helping us understand light as much as it's helping us understand electrons. So if you lower that frequency of light, the electrons come out with less kinetic energy. You see this y-axis is kinetic energy. As you're dropping down, they have less and less kinetic energy, and then you end up with no electrons coming out because the frequency is too low, the wavelength is too long. So if you get into the infrared, you don't really get any photoelectrons. You get into the visible UV, you get lots of photoelectrons. The slope of this line is Planck's constant. So once again, totally different experiment, Planck's constant shows up again. So we're finding that this Planck's constant is something fundamental to nature. And in fact, it's a way to convert the frequency of an oscillation, light, to the kinetic energy of the electron. So this is a way to convert frequency over to energy. And you can see that in the units. Okay, so Planck's constant, let me just go back a page. It's right there at the bottom. Where is it? Let me see. There it is. So if you look at the units, if I multiply this by frequency, which is cycles per second, the per second and the seconds cancel, and I end up with joules. So this Planck's constant converts frequency to energy, and we see that in the Planck equation. Now this led to this description of light as a stream of particles called photons. Because it makes sense, like billiard balls. A photon comes in with a certain energy, hits, and the electron gets bounced out. Okay. It also means that, it sort of prejudiced people against the idea that light was a wave. Think about being at the beach and body surfing, you're playing on the waves of the ocean. How absurd it would be. The wave's energy is sort of divided across the whole front of the wave. If that whole wave collapsed and it deposited its energy into you, the little boogie boarder, off you go. So it makes much more sense to think of it as a particle, right? You're standing in the ocean and then a big particle hits you and knocks you out of the water. So this is clear evidence that light is a particle, not a wave. Okay. We use this even to today. The photomultiplier tube detector in a lot of our instruments uses the photoelectric effect. So a highly negative voltage is placed on the photocathode. You can see that's labeled here in the notes. The photocathode, it's just ready to emit electrons. A light comes and gives it enough energy for that electron to shoot off. As soon as it shoots off, the electrons are negative, so it's attracted to a positive plate. It hits that plate, creates an electrical jolt, and the computer can count. Hey, a photon of light hit our detector. So that's how we use it. Now, a single electron doesn't cause a lot of an electrical jolt, and so we have a photomultiplier tube, multiplier. Okay, so we have this, it looks like a little vacuum tube. If we zoom in on that region right there, we see the different cascades of anodes. Okay, so light comes in from the top, hits the first one, which is the most negative, and an electron shoots off. But again, it'd be hard to detect a single electron, and so it hits another photocathode or cathode, and it's compared to another anode, and 2 or 3 electrons come off. So it's like dominoes, right? You just barely hit the first domino, and then off they go. And so then that one spits out 6 or 7 electrons, and then 100,000, and 200,000, and 1,000,000, and eventually you get like 1 billion electrons out of this photomultiplier tube at the end for every photon that hits. So it's a very sensitive detector. It's using the photoelectric effect. Low energy photons, what is this idea of this work function? If it doesn't have enough energy, it can't eject an electron. And so we can start to think of these things as energy levels. Okay, so this is an important concept. So everybody wake up and see, like label these are energy levels. So I'll just call this an energy level diagram. And that's really big. We use that all through the semester. In fact, a lot of the problems that you have in concepts, if you could draw the energy level diagram, you can understand this system. So we're going to use these the whole semester. And what we're saying is we can take that photon of light and convert it to an arrow of a certain length. If light has more energy, it'll be a longer arrow. If it's a less energy, it'll be a shorter arrow. So the arrows in these energy level diagrams are how light interacts with the system. So light comes in, it hits an electron on the metal surface, but it doesn't give it enough energy to escape. So that top level is the escape energy for that electron to escape the surface. If light doesn't give it enough energy, it can't escape. Okay. And also the Planck equation, the frequency is just the speed of light divided by the wavelength. So that's the relationship of frequency to wavelength. Okay. And so this is one of my trademark jokes that you guys will need to remember for the rest of your lives. Okay. So the Greek character for frequency is nu. Okay. So when you're walking across campus and someone says, "Hey, what's new?" You say C over lambda. Okay. And they'll go, "You've had DW, haven't you?" Yes. So that's it. What's new? C over lambda. Very good. Try again. What's new? C over lambda. Perfect. So you won't ever forget that. So you can put that in for nu, and you can see that the energy is hc over lambda, and you can convert energy in wavelength as well. Now we talk about wave numbers too, and so if you see this little tilde on a nu, we might call it frequency, but we really mean it's a frequency in wave numbers. So it's just 1 over the wavelength. So we deal with that as well quite a bit. Okay, so let's look now at high energy photons. So if light comes in with more energy than the escape velocity, so this is what's needed for escape, then where does that excess energy go? It goes into the kinetic energy of the electron. So higher frequency light has higher energy, and so then the electrons come out with more energy, and that's how we detect them. We detect their escape energies. And that's how we determine whether an electron came out of a 1s orbital or a 2s orbital or a 2p orbital, is how fast they're moving when they come out. We hit it with X-rays, so everybody has enough energy to leave. But the 2p electron comes out with a lot more kinetic energy than the 1s, because we had a harder time pulling the 1s away from the nucleus. So it comes out with less energy, less excess kinetic energy. Now, how would we detect the energies of electrons? It's pretty easy, same as we do on a highway curve. If you got a Ryder truck and a Porsche, which is going to turn faster? The Porsche, right? It's lighter weight, but let's say they all weigh the same and they're just going different velocities. So let's pick 2 Porsches. One's going 200 miles an hour and the other one's going 100 miles an hour. Which one's going to corner faster? The 100 mile. Because the 200 has more inertia, right? So it's going to have a larger arc, okay? And so we can take those electrons around an arc surface using charge. So the electrons come out of the surface, and we'll draw this later in the semester when we get to it. But we filter those electrons by their kinetic energy, and we know how much energy they had in the system. So that's a photoelectron spectroscopy. So the high energy light is sufficient to eject an electron, and it gives off electrons with different kinetic energy depending upon how tightly they were bound to the material. So what about waves? Well, this idea of electron or photons being particles was really cemented in quite well. It was also the opinion of Newton. So if you're going against Newton, you're going to have a tough time. So all of the scientists at this point were on Newton's side, saying that light was a particle. And Thomas Young used the wave theory of light to explain diffraction. So light can have diffraction waves when it goes through a small pinhole, and this was very easy to explain if light is a wave. So he presented a paper to the Royal Society, which was a prestigious group of scientists and mathematicians, and they said his theory was destitute of every species of merit, meaning it was worthless. And that's kind of a bad review, right? So he got roasted by these eminent scientists because he was going against Newton. And it was sad. I mean, he died, and like 100 years later, then it was shown that he was right. I mean, that's pretty sad situation. So 1927, they have another Solvay conference, and now we see some new names like Schrodinger and Pauli and Heisenberg. So these are some of the fathers of quantum mechanics. You still have Rutherford in there, but here these are now taking the physics to a new level by introducing the concepts of wave nature of nature. So here we also still have Einstein, we still have Madame Curie, and a bunch of other names that you probably recognize. So we've had black body radiation. It needed quantum mechanics to answer that. We had the photoelectric effect, which confirmed that Planck's constant was something fundamental to nature. We also had the emission spectra of atoms. So if you put hydrogen or any kind of atomic substance in one of these electric discharge tubes and ran it through a prism or a monochromator of some sort, you got line spectra. You got discrete lines that came out. Now, why are they lines? Well, because you have a slit here. So you have a sort of a vertical source. You have a slit that kind of cleans up the light right here. And so the image of that slit goes through this dispersing element and gives you these different lines on a photographic plate. So we still call these spectral peaks, we still call them lines to this day. So when we talk about spectral lines, we're talking about peaks in the spectrum. That's a huge concept in this course. So when you see a peak on a spectrum, you'll hear me call it a line, a spectral line, because it's just the language that we've used from Bunsen forward. Okay, so yeah, Bunsen invented this. He invented this spectrometer, spectrograph, but his name, the Bunsen burner, got his name, and this Bunsen burner can replace this electric discharge lamp. So you can do like a flame test for metals, and if you ran it through a spectrometer, you get a particular spectrum for that metal. So Bunsen, it's kind of sad. The spectrometer should be named the Bunsen spectrometer, but the little source, the flame thing, got named the Bunsen burner. So I don't know if he's mad about that. It probably all happened after he was dead. So let's look at atomic emission spectra. So this is the emission spectrum of hydrogen. Now, hydrogen is the simplest element there is. It's just one proton, one electron. Ought to be simple. Now, this is the emission spectrum. So this is the electron being excited and then de-excited. We don't have near enough energy in a Bunsen burner or electric discharge tube to do anything with the nucleus. So the only thing in hydrogen is an electron and a proton. They're attracted to each other. So when I excite it with a flame or an electric discharge, the electron gets further from the nucleus. And when I de-excite it or it emits light, the electron gets closer to the nucleus. That's the only thing that can happen. So conceptually, it's very easy to understand. I pull the electron away, I've got an excited atom. I let the electron go back down, it emits light, and I have a ground state or relaxed atom. Pretty easy concept. Why can it only have discrete energies, though? That's weird. Why does the electron have specific distances from the nucleus that it can be? That's the only answer we get from this spectrum. That the electron can be really far away, intermediately away, or really close to the nucleus, and that there's only discrete differences between those orbitals. We know they're orbitals now. We have 1s, 2s, 2p. But this is where that came from. This idea of orbitals came from that spectrum. You see, there's only 3 or 4 lines in the visible. There's some in the infrared and so on, some in the UV. Okay. And here's the emission spectrum of iron. Very much more complicated because you got a whole lot more electrons. Iron has 26 protons, so you got 26 electrons. We're going to learn about the electron configuration, so it's really complex, okay? But still discrete lines. If you run that through the spectrograph and through the photographic plate, you get these places where the electrons can emit light. So this is really bizarre. Newtonian physics could not explain this, and it led to the concept of orbitals. So this is the problem with the atomic world. the atom is not a tether ball. So you ever play tether ball? It's got a pole with the ball on a tether, and it can be at any angle as it orbits. So that ball can have any orbit. That's the classical physics mode. And they thought, well, the electron just orbits the nucleus, and it can have any diameter, but it can't. Okay. Another reason why it can is because as the electron's coiling around in a surface, it would be emitting light all the time. So anytime you have an electric charge that takes a turn, it emits electromagnetic radiation. So it would be losing energy the whole time, and it would just fall into the nucleus. So something keeps the electron out of the nucleus. If the electron's a particle, it would just get sucked into the nucleus. So I know we think of electrons, we talk of electrons as discrete particles, but they have to behave like waves or they would be sucked into the nucleus. So the Bohr atomic model treated the atom as a solar system with the sun in the middle, the nucleus, and the electron jumping in and out of those orbitals. It's kind of what I've already talked about. And so if we absorb light, the electron gets further from the nucleus, and then if it drops back down, you have the reverse reaction where it spits out a photon. Okay. So conceptually, this works. Physics-wise, it doesn't work. So an electron orbiting the nucleus would always be emitting light, and it would just get sucked into the nucleus as it slowed down. Okay. So there's a problem with this model. So de Broglie, in his dissertation, introduced the idea that the electron is not a discrete particle orbiting the nucleus, but behaving like a wave that's oscillating. Okay, so the wave has to be zero at the nucleus because if you're in a spherical polar coordinate system, there's no volume at the nucleus. So volume goes to zero at the nucleus, so it can't be at the nucleus. And then if it's going to be attached to the atom, it can't be at infinity. So the wave has to go to zero at infinity. But in between infinity and the nucleus, it has to be non-zero. And so this is a requirement of the waves of electrons around the nucleus, and it worked. Okay? So he said these are discrete standing waves, just like the strings of a violin have two fixed points where they have to be zero. They have to be zero at that end and at this end, and in the middle non-zero, or you don't have any waves. And so he said, let's use this mathematics to describe the electron around the nucleus. And Schrodinger did that. So this is the paper, 1926, where Schrodinger used this word undulatory theory of the mechanics of atoms and molecules. Undulatory means wave-like behavior. So he's pulling the mathematics of Thomas Young that was roasted by the Royal Society, the concept of standing waves from de Broglie, and he spent about 3 months. He had to call for help because he didn't have the math to do it. So that ought to make you feel comfortable. He had to reach out to a mathematician and say, help me with these differential equations. And it was like a burst of activity, and he solved the hydrogen atom spectrum. So these are the hydrogen atom spectral lines. And the top is the observed, and the bottom is the theoretical that he got from his mathematics. And so he was able to match even the fine structure. If you put this emission in like a magnetic field or an electric field, you get these hyperfine splittings of the electrons, spin up, spin down, and all of that. They didn't have the theories of the spin ups and spin downs. They had this idea of the electron connected to the nucleus and the standing waves, and he was able to solve that problem. And then Dirac took Schrodinger's math and extended it to multi-electron atoms like helium and lithium and so on. So Dirac is the one that's really, I guess, wrapped it all up in a nice package. And so in his paper, he had some really bold statements. So this was one of them. He said, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry. That's a bold claim. He's like, I've solved the math for all of chemistry. But the difficulty is the exact application of these laws leads to equations that are too complicated to be solved. And there are some parts of the math that we still to this day don't know how to solve. Okay? The interaction of the electron waves with each other is the one that we can't solve. It's called electron correlation. Okay. So then the very next sentence, it says, it becomes desirable that approximate methods applying quantum mechanics should be developed which lead to explanations of the main features of this complex theory without too much complication or computation. So that's that was the reason why I put a graduate student on it, Victoria Jackson, when she was here working on her master's thesis. I said, let's see if we can do all of quantum mechanics in one dimension with the particle in a box. Let's take the violin string idea and let's go all the way to spectroscopy, just like Schrodinger did. And so the very first assignment I gave her was like, you've got to go into the literature, all of the PChem books and everything to make sure no one's done this yet. And so, you know, she came to the group meeting after a week of searching and said, no one's done it yet. And I said, look again. Right? And then she did some more research, and the next week, no one's done it. I said, look again. So we went for weeks and weeks trying to find if this had been done anywhere else, and it had not. It's such a simple concept because, again, we're trying to do what Dirac said. Can we find a simple system that can help us view the math without too much complication? And so that's where the spectroscopy theory in one dimension came about. So she wrote it up in her thesis. We had about 80% of it done in her thesis, and then we finished it out and got a book. So yes, all right. So that was published a couple years ago. And so this was one of those things that I never really wanted to write a book because there's a lot of books, right? What's one more? Okay. But I realized that if I didn't get this written in a book, I wrote this book just to get it down because I figured if I retire or get hit by a bus, no one's going to teach it this way anymore. No one's going to have this simple theory of math. And so we're doing this for the first 3 weeks or 4 weeks of the course. So we're going through this in one dimension where you can do it by hand, you can do it on Excel, and you can understand what Gaussian's doing on the computer.
Thank you.
Yes, very good. All right. That warms my heart. Okay, so we're going to go through this in one dimension. So you're going to get sick of me talking about the particle in a box, but that's the simplest system. It's really just the violin string. And the particle, we use the word particle, but it's really a wave in a box. Okay, we're describing that particle with a wave. Simple sine function. Easy as peasy, right? Sine x. We can do that. I'm not afraid of sine x. I don't like triple integrals. So if we do the hydrogen atom, we got to do the integral related to the distance from the nucleus, r, then longitude and latitude, theta and phi. And it's crazy mess, okay? You'll have to do it in grad school. If you go on to grad school, you'll do the full hydrogen atom.
I'll get to it.
Yeah, there you go. So conceptually, how big is the atom related to the nucleus? So if this ball at Target, my kids, I'm sure they got tired of me. So we're walking along and going into Target, and I see that ball. I was like, whoa. They're like, what? It's a ball. And I said, what if that was a proton? Where would the electron be in a hydrogen atom? Okay. So when they say that nature is mostly space, this is what we're talking about. So if that were a proton, and you'll never go into Target again without seeing this proton sitting out front, how big would the 1s electron be in a hydrogen atom? Okay. It would go from Livingston to Navasota or Madisonville down to Spring. So it'd be a 71-mile diameter. So this explains a lot about chemistry and why we focus on the valence electrons on the periodic table. Because the hydrogen atoms, if I've got a hydrogen atom in Louisiana and it's moving towards Huntsville, the electrons are going to see each other 35 miles out. Or the nuclei will be 71 miles apart. And they'll start interacting. So it's the electrons that do the chemistry. Now, if you stay with me the whole year, at the end of the semester in the spring, we get into nuclear chemistry, and it's pretty crazy. We're the nuclear transformations. But at this point, I mean, from now until, I guess, April, all we talk about is the interactions of the electrons. The chemistry takes place related to the valence electrons in the molecule and the atoms. And now you know why. So in summary, these are the experiments that revealed the quantum world. We had the black body radiation and the UV catastrophe. Planck solved it with Boltzmann's discrete energy level assumption. Okay? And out of that came Planck's constant. Planck's constant was confirmed in the photoelectric effect as the energy slope. So frequency changed, Planck's constant converted to energy. Okay? Then we had this problem with atomic spectra. Okay, and these discrete lines. What is the electron doing around the nucleus in the hydrogen atom? We couldn't figure that out. And the wave nature of light and Planck's constant and quantized thinking fixed that problem. Schrodinger did that. And then Dirac applied it to larger atoms and molecules. So he pretty much solved, if you solve the electron cloud, you've solved all of chemistry. So that's why he was talking about solving all of chemistry. Why didn't he say we solved all of physics? Well, because we haven't merged quantum mechanics with general relativity, and we haven't figured out where it fits into the standard model of cosmology. So there's still open questions in physics, but all of chemistry, in terms of how the electrons react with each other, is mostly solved. The electron correlation is the only tiny piece of mathematics that we still don't know. So that's, now what's this cold temperature behavior and heat capacity? We had to go to the spring semester to talk about that one. So that's a little teaser, and that one was solved too. So the quantum jumping drove Erwin Schrodinger crazy. The electron hopping away from the nucleus and hopping back and spitting out light. And he wrote to a friend, if this damn quantum jumping were here to stay, I should be sorry I ever got involved. So I'm glad he got involved. It's been an amazing view of chemistry from the electron's perspective. And Bell's inequality experiments show that it even jumps faster than the speed of light, which breaks physics. So it's crazy. Yeah.
It has mass. You can't do that.
Yeah, I know. You can't do that, but it does. So anyway, there's more to learn. Y'all have a great day.